Okay, so now let's move back to physics, all right? So now you have basically learned everything you need to know about vectors, and even the hardest thing is the vector cross product, right? So just it's a little bit abstract, but just memorize the rule, and that it's not too difficult to implement. And I think the hardest thing is to visualize what does it do for you, the vector cross product. So hopefully now it will answer that question. You'll see why that abstract and convoluted way of multiplying, quote unquote, multiplying vectors has a use, all right? So we'll see. Okay, so torque is what I call, it's basically the angular version of force, of the concept of force, okay? So first of all, let me address the terminology issue. This is also known as, it's also called the moment of force, okay? Which it's an annoying terminology to me. It's my third least favorite terminology in physics. And sometimes even worse, people will just call it the moment. And that is more of an engineering term. Again, no offense to any engineers, but that is not the best of terms. This moment of inertia, so you have to call it moment of force. Yeah, taking moment, and then it's again very potentially confusing with moment of inertia. So don't call moment of inertia inertia. Don't call torque moment. So that you will live a happier life in general. So yeah, to avoid any confusion, we'll call it torque. But just to let you know, there are other terminologies as well. Okay, so what is it, right? So what was force? Well, force was basically something that causes acceleration, right? It's proportional to acceleration. So force is something that causes acceleration. So we should have an analog concept, well, which will denote tau, the Greek letter tau, that will be proportional to, not the best term, symbol as well. Technically, the alpha, I can never draw these correctly. And the proportional symbol is a little bit squeezier, a little bit thinner than the alpha. It's more round. It's like a curly A. You can Google what that is and look at a textbook or whatever for better images than this. Anyway, tau is proportional to alpha. So angular acceleration, right? So torque is what should cause angular acceleration, just as force causes acceleration. So what's angular acceleration? It's how fast, right? Let's actually put it here. That is defined as, yeah, this is the definition, right? Is how fast does the angular speed changes. And as we motivate it, right? So now you can, let's try to come up with we know the relationship between this and this. But we now kind of want to relate this with this, okay? So this guy should kind of be related to F, because if I push an object here, we know that sort of at this point, if you have a force that goes through the center of mass, the object will not rotate, but it kind of depends on, let's make this a rod like this. So if you push it here, it doesn't rotate, but it kind of depends how fast it rotates with the same magnitude of force. Well, the harder you push, first of all, off center, let's say R, distance R off center. Yeah, so this guy should be proportional to F, right? So the larger the force, the faster you will be able to accelerate. At first, the omega naught is 0, it's not rotating, and you want some non-zero, you want it to increase to omega final, right? So the larger the force you push, this guy should accelerate more. So tau should be related to F, and also it should also be proportional to the distance away from the center of mass. So this is the displacement from the center. Okay, so it's this vector from the center of mass. Okay, so the displacement from center of mass, let me just use a shorthand over here. Displacement from center of mass, and F like this. I'll just talk about the magnitude. So technically I could say distance, but the fact that I don't have a vector sign, it's magnitude. So these are just scalars, that's fine. So this, I'll remove the dot as well to avoid confusion. So it's just scalar multiply. And we basically define torque as this, okay? But I won't quite write the definition symbol just yet because there's a little bit more to this, okay? So this is the fundamental concept. Torque is basically force times displacement from center of mass. Don't just say displacement, because displacement from where, right? So you want to be precise. So displacement from the center of mass. You need the origin to talk about that. Okay. Now let's see why is this not the full definition, and why we need to upgrade it a little bit. But first of all, you already sort of get intuition that if you try to open the door again at the hinge over here, like try to open it, right? So if you want to push it at different points, so this is the displacement vector from the center oh sorry, yeah, from I shouldn't say center of mass, it's from the rotational axis. So why not the center of mass? Because if, let's say, you have friction, you have a ball on the ground, even if I push it in the center of mass, it will start rotating, right? If you have a football over here, you push it, or a basketball, let's say, you push it through the center of mass, it will still rotate. So what's going on is because it's rotating about this axis. So it's, if you can imagine, right? The reason is this friction over here. You push it and friction doesn't want to go. It's kind of resisting it. So you kind of see there's a disagreement over there, right? So it will start rotating. It's only center of mass. It's only rotating about the center of mass if this is in space. So that was free of any extra force. So in this case, there's a force of friction this way, and there's a force of push this way. Right. So that's where it causes a discontinuity, and this is the pivot or the axis of rotation, or the fulcrum. All mean the same thing. Okay. All right. Yeah. So this is the axis of rotation for the door. If you apply a force over here, right, with the same magnitude, why is it more beneficial to push it towards the edge? Is because the displacement from the rotational axis, or the distance from the rotational axis, is larger. Okay. Now, now let's upgrade this a little bit. If I push it perpendicular, all things is good in the world. Right? If I push it perpendicular here, but what if I push it? What if I push it this way? Okay. If I apply a force this way, is that going to give me a large torque or a small torque compared to the same length? Let's see if I can make that the same length of force vertically downward. Which one will be more helpful? If I push the door sort of sideways or push it perpendicular to the door? Well, you understand it's perpendicular, right? Your intuition is like that. So what's going on? And what's going on is, let's actually ask a simpler question. If I push it straight towards the fulcrum, towards the pivot over here, towards the axis, and apply a force there, will I be able to open the door? Right? If you push it that way, no, you won't. So what's happening if you push it sideways like this is you have a perpendicular component. So let's say this is the original force. You can resolve it. I'll use a thicker arrow as the resolved components, right? So you can resolve it into a component that is perpendicular, so like a perpendicular, and a component that is parallel. So this is F parallel to the displacement vector. Parallel to what? Parallel to R. Okay. So yeah, let's call this R, right? So this is parallel to the displacement vector of the rotation axis, and you're pushing at this point, right? So there's R, there's F, there's each of the components. Which component, is it the parallel one or the perpendicular one that's going to open the door for you? It's the perpendicular one, right? This guy's not going to do anything for you in terms of opening the door, right? So let's see. So this is R. Let's try to compare F and R. In fact, let me draw it over there. Okay, and because I want to push the force in a different direction. Okay, so this is the axis of rotation, and this is the point of contact that I'm pushing. And let's say I'm pushing it here just to keep things a little simpler first. So that's the force, and this is R. But in order to compare R and F, you need to have them start at the same point. So I'm going to move, since this is the point of interest, this is the point of contact, I'm going to move the R vector over here, okay? And at the same time, I'm going to resolve the F. Yeah, let me make these red because I'm most interested in these two, right? So this is F, and this is the R vector. And this is the common, I'm putting them together. This is the general rule to deal with vectors. Whenever you want to add, subtract, whatever, put them together at the same starting point before you start doing anything. And let's resolve this guy along this axis and this axis. Right? The X, we'll call this XY axis like this. And in this case, we have F perpendicular to the door and F parallel to the door. Okay, and now, what is the included angle between F and R? So I want to use different colors. That's the included angle. Which one is the which is the component of F that is opening the door again? F parallel is not really opening the door, right? So if I push it at an angle like this, really, it's only that component that is really helping me. And how is this component related to the magnitude of F? Well, that's this one, right? So it's not the one that is sandwiching the theta. So this guy is sine. So this is F sine theta, right? So theta being the included angle, included in what? Included in R and F, right? So that's what we're comparing, the displacement vector from the axis of rotation and versus the force, okay? All right, so what is the torque? The torque, the curly T, is only this part that's opening the door, right? So it's F sine theta times R, okay? Because I can even make this a vector and say, hey, this guy is this guy plus this guy. So I can actually call this a vector and this a vector, right? So this vector plus this vector is this vector, right? So you agree. Now, the one that is really contributing to opening the door is this guy. So when you're talking about opening the door, tau should be this guy's magnitude times R, okay? Which means is if this is only part of the component of my original force, this is this, like this, all right? Now, all right, good. So it's in some sense, you're taking the parallel component of the force and R, all right, so we understand that. You can call this the second version of it. You can say this is the original definition and it's the force sine theta, force times R, but you need to include the sine theta, that's the angle between the force vector and R vector like this. So that's the second version of the definition, a little bit more precise than just force, because originally if I just say, hey, tau equals FR, but it depends on the direction, right? You need this guy to be perpendicular to R for you to have a torque. Otherwise, if it's parallel to R, you will not have a torque, okay? So this is the more accurate one. And can you notice this combination? Does it ring a bell of what we just learned? Yeah, that looks like the magnitude of some guy's cross product. Which guy's cross product? Well, F and R, right? So this precisely looks like the cross product between S and R, F and R, like that. That's why it's useful, all right? So this is the magnitude of torque. So maybe torque can be a vector, right? Clearly, R and F is a vector. We know that since day one, or lecture 2 or 3. We know that force is a vector, right? but now it looks like torque can be a vector as well, right? So this suggests that torque is F cross R. Turns out this doesn't really tell you which way it should go. Turns out this is the correct way, all right? What do I mean by correct way? And this is the most general definition. I'll put this in a box. I'll also put this 2 in the box. Maybe this one, yeah. And so because you can sort of get this one from here, if you look at the magnitude, right? Now that you understand what cross products is, the cross product of this is the magnitude of F times magnitude of F, it's the sine of the included angle. All right, so this is the vector version of this. So it's, in fact, this is the most general one, okay? So why is this the right direction? Let's see, right? If I do R cross F, look at the 2 red vectors over there. Use your right hand rule and tell me, is it into the board or out of the board when you do R cross F? It's into the board, right? So R cross F, it's either, we need the resultant vector to be either out or in, right? So when you point your thumb outwards, you can barely wrap your way, you need to wrap it the long way around from R to F. But if you point the thumb inwards, it's just this to this, all right? So it's easier. So it's inwards. Okay, so you see which way is your right hand sort of swiping? It's swiping in clockwise or counterclockwise? Clockwise, right? And that is precisely what the door is going to move at. So let's be precise. Is this cross this will create a torque pointing. So the torque vector is going to point into the board, into the page. Okay. So torque is into the page, and that means it's a rotation in this direction in R cross F direction, right? The door will open this way. And if this is proportional to angular acceleration, which we'll see later on, then, right, which way will the door accelerate? Initially, it was, what's the angular velocity? Initially, it was 0. So which you want it to sort of increase, right? To not 0, so you need to accelerate. So you want it to accelerate this way, because if you push it like this, push it with this red force, it will accelerate, the door will accelerate this way. So you want an alpha that is in this clockwise direction, which means the alpha vector should go into the board. And now you see sort of they match. R cross F will give you the magnitude, right? So the magnitude will give you the correct magnitude, and right, it will give you, so this is what the motivation is, but this is sort of the more general one, and the direction. So this is when you take the magnitude, it'll tell you the magnitude of the torque. The direction will tell you the direction of rotation. Okay, so it's really the right hand will tell you that. Okay, all right. So just like what we'll see in the next video is force. There is Newton's first law, second law, and third law. And believe it or not, those 3 laws applies to torque as well. And we'll basically see the angular version of it. All I need to do is change the F into tau, and you can see what applications there are. Okay.